السلام عليكم ورحمة الله وبركاته. أسعد الله صباحكم يا شباب. اليوم إن شاء الله مكملين معاكم من هذا السلايد. المرة الماضية وصلنا لهذا السلايد وحكينا عنه. في عنا ال BV diagram. هنا هون بهذا السلايد two diagrams. Okay, so this is BV diagram and here is the same, but the difference is in terms of freezing. Okay, so the BV diagram, this one, okay, of a substance that contracts on freezing. Okay, وبنقدر نشوف كيف هدول اللاينز vertical. Okay, and the other types of material that are expand on freezing such as water. So دائما لما بدنا نرسم ال VV diagram حنرسم ال temperatures line. هذول اللاينز حنرسمهم ايش؟ constant. اوكي. في ملاحظة ثانية على هذول الدياجرامز، سواء كنا بنحكي عن هذا أو هذا نفس الإشي، اللي هو هذا اللاين. إذا ملاحظين هذا اللاين اسمه إيش؟ التريبل لاين. أو إيش المقصود بالتريبل لاين؟ التريبل لاين المقصود فيه إنه عندي 3 phases، triple phases. أوكي، اللي هم السوليد والغاز والليكويد بيظهروا at the same time. أوكي، على هذا اللاين إذا أنا محقق شروط هذا اللاين. إيش شروط هذا اللاين؟ constant temperature. حكينا هذول اللاينز يمثلوا T. So along this line we have constant temperature and we have constant pressure. Okay, so B constant. Again we have temperature constant, but the volume is vary. Okay, so we transfer from V1 to V2. Okay, but why it's named triple phase or triple line? Because we have 3 phases. Okay, so هذا بنشوفه as a line on a BV diagram. هلا لو انتقلت ورحت لدياجرام ثاني زي ال BT diagram، هذا اللاين triple line بصير بظهر وكأنه ايش؟ نقطة، فبسميه triple point. So triple point ايش المقصود فيها؟ هي النقطة اللي بظهر فيها 3 phase together. Okay, الsolid phase والliquid phase. Okay, وهذه منطقة الفيبر phase. So at this instance بظهر عندي 3 phases. Okay, so هذا ال BT diagram وهذه هي triple point. So under some condition so what's the meaning of triple point? All 3 phases of substance coexist in equilibrium at state along the triple line. Okay, the states on the triple line, so اللي هو هذا اللاين اللي هو بحالة ال BV diagram. The states on the triple line of a substance have same pressure and same temperature but different volume زي ما حكينا. The triple line appears as a point on a BT diagram. The triple point of a certain substance like water occurs at temperature 0.01 and at pressure 0.6113. So the thing that you know is the boiling or the transferring point or condition for water is at 100 degrees Celsius. Okay, but this is true only for atmospheric pressure. Now if we're lowering the pressure up to 0.6, then the boiling temperature will be 0.01. Okay, okay, so here is, yeah, this is the BT. Another name for the BT diagram is the phase diagram. Why they call it phase diagram? Because we can notice the transformation between any two phases. Okay, so for example, if we are transferring from solid to liquid, then we must cross the melting line. Okay, if we are transferring from, or we have phase change from liquid to vapor, then we must pass through the vaporization line. And if we want to transfer from solid to vapor, for example, so we must cross the sublimation line. Okay, and here is the description for this diagram. As a summary for the diagrams, we have BV diagram. Okay, and we have TV diagram, and we have VT diagram. Okay, and this is the 3D view of those diagrams. Actually, in this portion of this material, we are interested in PV diagram and in TV diagram. Okay, this diagram is not very important in this course. Okay, but at least you have to know its name, why it's named like this. Okay, etc. So the only theory part. Okay, another important property in this course is the enthalpy. Okay, enthalpy, and its symbol is H in uppercase or H in lowercase. In this analysis of certain types of processes, particularly in power generation and refrigeration, do you remember those cycles, power generation and refrigeration cycle? We mentioned that we have 4 components in each cycle, and there is inlet and outlet. Okay, so inlet and outlet, that means we have flow, we have mass in, mass out on those cycles. Remember, we have compressor, turbine. Okay, so we have inlet outlet as a mass, including the energy and in terms of Q and W. Okay, so the best property to describe the mass, the energy of the mass inlet and outlet is the enthalpy. We frequently encounter the combination of internal energy and the pressure volume product, PV, or they call it flow energy. Okay, so if there is flow energy into the system, and of course we'll have internal energy, so the summation between them is the enthalpy. So this term usually we call it flow energy, and this is the internal energy. The combination is the enthalpy. Okay, this is in uppercase, and their units is joule, or it is in lowercase and their units is joule per kilogram for all terms. Okay. Saturated liquid and uh, saturated vapor state stable. So here, from this slide onward, we'll start talking about tables or thermodynamic tables. Okay, and we'll start with the first region, and we call this region is saturated mixture liquid vapor region, or we can say saturated liquid and saturated vapor states. Okay, so saturated mixture. The saturated liquid vapor mixture, here is the name of this region, falls under the PV or TV dome. Remember, we said we have a dome, this dome, okay, this one. We have here critical point. This line we name it as saturated liquid line. This line we call it saturated vapor line. And the area under this dome, we call it what? Saturated liquid vapor mixture. Okay, and if we have a line like this, so this is TV diagram, okay, and this line represents constant pressure, then the intercept between the constant line pressure and this line, we must know that this state is liquid phase, okay, and the intercept here represent the vapor phase or gas phase, okay, and the points between them is the mixture, okay. So its properties can be obtained from water table. For example, if we are talking about water, okay, so any points lies underneath this dome, we can find it from the saturated liquid vapor mixture tables, okay. So for example, here in this table, its name is saturated water. So saturated means we are in the saturated mixture region. Okay, this is the meaning of saturated. We are under the dome. Any points under the dome and includes the line. Okay, everything in this dome. Okay, inside this dome and including its boundary. Okay, now which substance? Water. So we can understand what's inside this table from its caption, from its title. Now, this table special for temperature. So temperature here is independent property. We'll start with this property as you can see here. In the first column, we start with the temperature as a given information. Now, the second column is represent the saturated pressure. Actually, in the saturated tables, we have two tables. We have saturated table for temperature, if we start with temperature, and we have another table, saturated, but we'll start with pressure. So if we start with the pressures, the second column name is saturated temperature, the other property. Okay, so let's go back to the temperature table. So if we start with the temperature table, then any column after this column, its name is saturated. Saturated. Okay, saturated everywhere. Okay. Okay, and here is the units. This is in Celsius. Okay, as I mentioned earlier, the first 50 page for SI units. Okay, so here pressure is kilopascal. Here meter cube per kilogram because this is specific volume. Here we have specific internal energy, but they did not name it as specific. Okay, but you can tell from the units, kilojoule per kilogram. So, and here is the lowercase. So here in the first column, for example, we are talking about liquid phase, and instead of L, we give a subscript F. Okay, so either VF in some references or VL. It means the liquid phase. Okay, the liquid phase. And if we have gas phase, then you will see this subscript VG. Okay. Now here saturated liquid, and here we have saturated vapor, and here we have the difference between them. I'll talk about this later. And this slide I will talk about. So in table pressure is lifted on the left. Here is we start with the pressure because its name is pressure table, and this represent an independent variable. So this is independent, and all the property are dependent on the value of pressure. Okay. So what's the difference between these two tables? Nothing. Okay. Use whichever table is convenient. Okay. Whichever table is convenient. So we can start with any table. But if we have, for example, temperature like 24 or 28.96, we cannot go to the temperature table. We cannot, because 28.96 is between these two values. Okay, 28.96 between these two values. So we cannot start with the temperature table. So it's better to go to the pressure table. Okay, so try to find exact value. For example, if we have a 28 and we have pressure 4, so it's much better to start with the pressure table because we are looking for exact value. If not, then we'll do interpolation. Okay, I'll talk later on about interpolation, but I believe you know what's the meaning of interpolation. Now, sometimes we'll see property like this: UFG, HFG. Here we have UFG. What's the meaning of this value? For example, HFG, the enthalpy of vaporization or latent heat. This is, for example, if we are in pressure 1.5, then the amount of energy responsible of transformation from liquid to vapor is this amount. Okay, and you can easily this is internal, sorry. And you can easily calculate this value by subtraction 2339 from 54. Okay, you will get this value. So either you subtract them, okay, either subtract them, or you can take this value readily for you. The amount of energy needed to vaporize a unit mass of saturated liquid at a given temperature or a pressure is called the HFG. Okay, so this is the meaning of HFG, the latent heat. Okay, let's see examples on how to use the tables. Okay, let's start with example 1. So here is example 1. We have a rigid tank. Okay, a rigid tank will understand from this word that we have constant volume. So V equal to constant amount. Contains 50 kilograms, so this is the mass, of saturated liquid water. So here is the phase, or I can name it saturated liquid phase. This is phase. Okay, and this is the substance. So we'll go to the water table, substance. Okay, at 90 degrees Celsius, so this is Tsat or T. Okay, determine the pressure in the tank and the volume of the tank. Okay, so what we'll do, I'll go to the saturated table. So here is the table. So here is the name of this table and the model, engineering thermodynamic appendix, first 50 page. Why first 50 page? Because the first 50 page for SI unit. Okay, so here it is, SI units, property table and charts. Now what do we have? We have certain tables, okay, from table A1 up to A3. Then in table A4 we'll have water substance. Water substance. How many tables for water? So 1, 2, 3, 4, 5, 6, 7. So we have 7 tables for water. Okay. The other tables for other substance. Here, for example, we have refrigerant 134A. Okay. And here we have certain tables for air. Here we have nitrogen. Here we have oxygen, etc. Okay. So we are interested now in the table A4 up to A7. Okay, from A4 up to A7. This is the most important tables so far. Okay, so what do we have here? Table A4, we have saturated water, and we'll start the first column with temperature column. Okay, so this is temperature table for saturated phase. Here we have pressure table for saturated. So we have 2 tables for saturated region, which is the area under the dome. Now here we have 1 table for superheated water, and here we have 1 table for compressed liquid water. Here is the area beside to the right of the dome. Here this is the area to the left of the dome. Okay, we'll come to this. Right. So we'll go to table A4. Okay, here is the table A4. So this is table A4, saturated water temperature table on page 916. Okay, and we'll start as we mentioned with the temperature. Let me use pencil. We'll start with the temperature. Okay, column. And then we have a specific volume, we have a specific internal energy, we have a specific enthalpy, we have a specific entropy, but we'll not talk about entropy. Okay, we'll talk about enthalpy and why it's specific, because its unit is kilojoule per kilogram. Here the same, and here the same. Okay, and you can notice that we have this property here. We have HFG and we have SFG. Okay, but we don't have VFG. But we can calculate it by subtracting this value from this value, so we can get VFG. Why it is necessary, we'll see in the coming slide. Okay, now let's go back to the problem that we have. So here is the problem. Here we have a rigid tank contains 50 kilogram of saturated liquid water at 90 degrees Celsius. So we'll go to the table, okay, and we look to the saturated water table, because he mentioned that the phase description is saturated and the substance is water. And he gave us an information. He gives us information about temperature, which is 90. So I'll start with the temperature table. Okay. Okay. Now I look for 90 degree. So here is the temperature column. I will go until I found this is 90 degrees Celsius. Okay. So I interested of this line. So what do I need from this line? So he asks about to determine the pressure in the tank. So this is the given information. We have 90 degrees Celsius. Okay. We have V constant. What else? We have mass of the liquid inside this tank, which is 50. Okay, what else? We have saturated liquid. So any property we need it from this table, it must be, if we are talking about V, it must be VF. If I need H, it must be HF. Okay, if I need U, it must be UF, because it's mentioned that here we have liquid. Okay, it's mentioned that we have liquid. So all property must be in liquid phase. Okay, so if we go directly to the table, we must say that at temperature 90, V sat, or B here in this example, must equal B sat from the table, and it must be equal to, so let me find it, it must equal to this value. Okay, so at temperature 90, here is the corresponding pressure, 70.183. So this is 70.183 kilopascal. Now the corresponding volume, calculate the volume of the tank. Okay, I need the volume, and it's mentioned that the volume is constant. So the volume here equal to mass multiplied by specific volume for which phase? For liquid phase. So mass is 50, and VF from table equal to, so here is V. Okay, I'll go straight forward until I reach 90 degrees Celsius. So here is corresponding VF value, 0.001036. Okay, 0.001036, and this is equal to, so let me use my calculator, multiplied multiplied by 50, and this is 0.0518. 0.0518. And the unit is meter cube. Okay, so here is the final answer. See. Okay, let's see another example on how to use the thermodynamic tables. Here we have piston cylinder, again closed system. Okay, contains 0.056 meter cube, and this is the volume of the substance contained in the piston cylinder of saturated water vapor. So this is the substance. Again, we use water. Saturated vapor means we are in the saturated table, and the phase is gas. So we'll look, if we need property, we'll choose, for example, Vg, we'll choose Hg, we'll choose Ug. Okay, if I need any property. This is the meaning of saturated vapor. So the given information is this amount is saturated vapor at this pressure, 345 kilopascal pressure. So this is the saturated pressure, 345 kilopascal. Okay. Determine the temperature. So the corresponding temperature, we need the temperature, and this temperature must equal Tsat. Why? Because it's mentioned that the state is saturated. And the mass of the vapor inside the cylinder. So we need also to find the corresponding mass. So let's go to the table. So this is the table A4. But in the statement of the problem, he gave us information about pressure table. So the temperature table is not needed. So we'll go down until I found table A5, which is a pressure table. Here it is, pressure table, and this is pressure. Okay, for water in saturated condition. Okay, so now we'll look to the value of 345. So this is 100, 200, and the value is 300, 345. So do we have it exact? Where it is between these two values. Okay, so here the corresponding value 3, 4, 5. So it is not exact. So we need to do interpolation. So how we do interpolation? Because I need, what do I need from this table? I need the Vg. Why Vg? So let's first go down until I reach the corresponding value. So here is our value. It's unknown and it's between two values. Okay. So now from this table I will pick those values. Okay, so I'm interested in to find the values corresponding to 345, which is unknown. It is here, somewhere here, between these two values. So the corresponding value for 325 is this one, and the corresponding value for 350 is, oops, is this one. So let me go to the solving board and write the corresponding values. Okay, so here is the solving board. So what I'll do is I'll write the values. So here is the pressure in kilopascal, of course. Okay, and we have another column which is Vg, and its unit is meter cube per kilogram. Okay, here how many states we have? We have state 1, state 2, and state 3. Or they are not state, we have 3 values. We need 3 values. Actually, my concern is the corresponding Vg value corresponds to the 3, 4, 5. So this value is unknown as we mentioned earlier. But in the table, we have this value is between 2 values, which is 325, and this is 350. We have corresponding value Vg, which is 0.56199, and we have another value corresponds to this value, which is 0.52422. Now we need to find this value. How to find it? By doing interpolation. So the interpolation states that this unknown value equal to, now here we have fraction, this fraction multiplied by certain values subtract from each other, and then the whole bracket added to a certain value. Okay, now what do we have? Okay, later on I will show you the exact equation for this one, but I'll teach you how to do it very fast, okay, even while using your calculator. So here in the fraction you have to subtract this value. Let me give it a name, y2, and this is y1, here x1, and this is x2. This is x2. So here in this fraction what we'll do y2 minus y1 divided by x2 minus x1 multiplied by x minus x1. What is x? This is x, and here is the corresponding value y. Okay, so x minus x1, and at the end this is a plus y1. Okay, so what we'll write? We'll write y, the corresponding value, equal to y2, which is 0.52422. This is minus 0.56199, okay, divided by x2, which is 350, minus 325. This bracket multiplied by x, which is 345, minus x1, which is 325. Okay, all of them added to, this is plus y1, which is 0.56199. Okay, and the answer here, y equal to, so 0.52422 minus 0.56199 divided by 25. This is multiplied by 20, and at the end plus 0.56199. So the answer is 0.53177. This is meter cube per kilogram. So here is the answer. So if I go back to the slide, so at temperature 3, 4, at pressure 3, 4, 5, the corresponding determine the temperature as well, okay, and the mass. So what we do is to find Vg. Why we find Vg, which is 0.53177? Because we need to find the mass, okay? Because mass here is equal to V capital divided by Vg, okay? V capital here is 0.056, and we could find Vg, which is 0.5, sorry. Let me use laser. 0.53177, and this is equal to, so 0.05 divided by, so this is 0.105. 0.01, 0.105, 3 kilogram. Okay. Now the remaining is to find the temperature. How to find temperature? We'll do the same. Okay. We'll do the same. So we'll go to the tables. Here is the table. And instead of looking to the volume, we look at the temperature column. Okay, here is the temperature column. So we'll go down until we reach the corresponding value. So the temperature is between 136 and 138. So I'll go to the solving board. Here is the solving board. Okay. So let me go down. I'll do interpolation again between pressure. So here is the pressure, and we have temperature. Okay. We have two values in top of and bottom of 345. Oops. 345. Okay. So, and here is the corresponding value, which is unknown. So again, we have here the value 325, and here 350. Here the corresponding value is 136.27, and the corresponding value for 350 is 138.86. Okay, so here again we'll do interpolation in order to find the missing value. So what we'll do, so the missing value is equal to Now we have fraction, the subtraction y2 minus y1, or 138.86 minus 136.27 divided by 350 minus 325 multiplied by 345 minus 325, all of them added to plus y1, which is 136.27. So the value is t equal to, let me use my calculator, 138.86 minus 136.27 minus 4 divided by 25 multiplied by 20 plus 136.27, and the answer is 138.342 degrees Celsius. Okay, which is very close to whom? To this value. Okay, because 345 almost the same according to this value. Okay, now let me go back to the PowerPoint and write down the result, which is 138.342 degrees Celsius. Okay, and the correct value is the same. Okay, guys. Okay, another example. So I leave this example for you. Okay, if you have any question, please ask me any question. Okay, so this question I leave it for you. So if you have any question, please raise your question to me. Okay, so here is another example. Let us see this example together. So example 3, I leave it for you. Let us see this example. So here what do we have? We have a vertical piston cylinder assembly contains 0.05. So this is mass of refrigerant 234A. So here is the substance. This is substance. Initially saturated vapor. So initially we can understand that we have two states, or we have more than two states. So this is phase or state 1. State 1, we have saturated vapor, so any property must be in the vapor phase gas. Is placed on a hot plate. Due to the weight of the piston, the surrounding atmospheric pressure, the pressure of R3134A is 1.4 bars. Okay. Heating occurs slowly, and the R134A expand to at a constant pressure until the final temperature is 20 degrees Celsius. Okay, do you know what? I leave this question up to next lecture. So meanwhile, you will try to solve example 3. Okay, and then we'll continue with the part 2 of this chapter. Okay, so we'll solve this example next lecture, and then we'll move to the next